The room is dim, the screens glow green, and a lonely spacecraft is turning its camera back toward the warmth it left behind. Voyager 1. In the next few minutes, it will send home a farewell view from the edge of the planets, and what it captures will shape how we picture our place in the dark for decades to come. Stay close to this channel for stories like this, and you will catch the quiet turning points that change how the universe looks forever. No engine sound reaches the room, no shaking floor, only numbers, light, and waiting. Out beyond Neptune, more than 3.7 billion miles from the Sun, a machine about the size of a small car is doing something almost human. It is looking over its shoulder. What it sees is not grand in the way people expect. The planets do not fill the frame. Earth is not a bright jewel. Home is a dust fleck in a sunbeam, a tiny crescent lost in scattered light. And yet this almost missed picture becomes one of the most famous images ever made. Most people think that is where the story ends. Voyager takes one last photo, powers down its cameras, and drifts into a silence too deep for pictures. But the deeper story is stranger than that, because the last image Voyager 1 will ever send back to Earth may not be the one most people think it is. To see why this matters, we need to step back. Most people believe Voyager 1 took its final image in 1990, its cameras shut forever, and from then on it became little more than an old radio beacon moving into the cold. That version feels complete, it feels final. It also leaves out the part of the story that matters most. Voyager 1 began as a machine built for motion and timing. It launched on September 5, 1977, just after its twin, Voyager 2, from Cape Canaveral. The two craft were sent into space during a rare lineup of the outer planets, a once-in-many-lifetimes chance to visit several giant worlds on one long route. Engineers knew they were aiming at a door that would not stay open forever. At launch, Voyager was not elegant in the way a movie spaceship is elegant. It was all booms, dishes, boxes, wires, and purpose. NASA says each Voyager weighed about as much as a subcompact car. It carried cameras, sensors, a golden record, and the kind of tough simplicity that comes from 1970s engineering. It was built to survive, not to charm. Then it got to Jupiter, and charm happened anyway. Voyager 1 began studying the giant planet in 1978 and rushed past it in March 1979. It found a faint ring around Jupiter and two new moons, Thebe and Metis. The closer it came, the less the solar system looked finished, and the more it looked alive. Jupiter was not a still marble. It was a storm machine. Its clouds twisted like cream pulled through coffee. Its moons were not dead little stones either. Worlds that had been dots in telescopes began to feel rough, icy, cracked, and volcanic, as if someone had turned on the lights in a room we thought was empty. Then came Saturn in November 1980, and again the old map broke apart. Voyager 1 found new moons there too, along with a new ring and finer ring structures than many scientists expected. It looked at Titan, Saturn's largest moon, and found a thick atmosphere rich in nitrogen. A moon had weather. A moon had chemistry. A moon hit a surface nobody could yet see. By then, Voyager 1 had already become more than a camera. It was a traveler that kept forcing adults to admit that the solar system was not as tidy as their textbooks had promised. That matters here because the habit of this mission was never to confirm the simple picture. Its habit was to leave the simple picture behind. Still, when people remember Voyager, they usually remember the photos. They remember the pale clouds of Jupiter, the rings of Saturn, and the golden record that gave the mission a human heartbeat. Carl Sagan, a member of the Voyager science team, helped the public feel that heartbeat. He understood that a machine could collect data and still carry feeling. After Saturn, Voyager 1 did something quiet but important. It turned north, out of the flat plane where the planets move around the Sun. Because of the path needed for its close look at Titan, it would not go on to Uranus and Neptune. Voyager 2 would take that road instead. Voyager 1 was already leaving the familiar neighborhood. That change in direction also changed its job. The close-up planet hunter was becoming something rarer. It would keep going past the worlds that filled calendars and posters and classroom walls. It would go where sunlight thins, where the sun's influence weakens, and where no human-made object had ever worked before. By 1990, Voyager 1 was about 40 astronomical units from the Sun. That means about 40 times the distance between Earth and the Sun. Out there, the light is weak and hard. The planets look small. Commands crawl across space for hours before the spacecraft even hears them. Every choice starts to feel expensive. And that is when the idea came back. Turn the camera around. Look homeward. Take the family portrait. Not everyone loved the plan. There was concern about sunlight entering the camera, there were worries about wasting power and memory, but the thought kept pulling at the mission team because nobody had ever seen the solar system from that far back. What Voyager made in February 1990 was not one single neat frame. It was a sequence, around 60 images used to assemble the first family portrait of our solar system. Voyager saw Venus, Earth, Jupiter, Saturn, Uranus, and Neptune. Mercury was too close to the sun to catch clearly. Mars was lost in scattered sunlight. Pluto was too tiny and dim. Earth was almost nothing. NASA later described it as a crescent about a pixel wide. In the image that became known as the pale blue dot, our world sits inside a stray beam of sunlight, as if even the camera had trouble finding us. That tiny point would later inspire Sagan's book Pale Blue Dot, and one of the most quoted reflections in science writing. The family portrait was not just moving because it was beautiful. It was moving because it shrank the argument. Every border, every war, every crowded city and lonely farm and birthday and goodbye sat inside that faint point. In 2018, NASA science leader Thomas Zurbuchen called the family portrait a symbol of exploration that lets us see our world in a new and bigger way. Then, at 5:22 GMT on February 14, 1990, Voyager 1 powered off its cameras forever. NASA later made the reason plain. The mission needed to save power and memory for the instruments more likely to matter in the deep journey ahead, especially the ones built to sense particles and fields. The camera software was eventually removed. The ground systems for reading those images did not last either. That sounds like an ending because in one clear sense it was. If by image we mean photograph, then yes, the story closes there. No more moons filling the frame, no more planets hanging like lamps, no more chance for Voyager 1 to surprise us with a fresh picture of a world we can point to with our finger in the night sky. It is easy to stop there and feel satisfied. Old spacecraft, final photo, beautiful goodbye. The machine did its looking and put its eyes away. By the time most people meet Voyager 1 in a book or a video, that is the version they inherit. The famous image becomes the whole meaning of the mission. And that is why the next part works so well on us. We think we know what counts as seeing. We think a camera is an eye, and anything without a camera is blind. We think Voyager's last image is safely behind us, framed on a wall, already finished. We think the rest is only distance. But that picture is about to change. The photograph was real, and the goodbye was real, but both were smaller than the story that followed. What we have just taken for granted turns out to be only the visible edge of a much larger act of seeing. Write the moment your idea of Voyager shifts in the comments below. That one detail helps this channel build the next story around the exact turn that caught you by surprise. The years after 1990 did not feel dramatic from Earth. No new postcard came home. No planet filled the news. Voyager 1 just kept moving, year after year, farther into a place with no landmarks people could sketch. If you were not paying attention, it looked like the mission had become little more than a dot sending numbers. But those numbers were not empty. Long before the cameras went dark, mission planners had already decided which instruments mattered most for the long road out. They knew the interesting part ahead would not be scenery and sunlight. It would be the shape of the sun's outer reach, the stream of charged particles blowing outward, and the place where that stream finally loses its grip. Most of us imagine the edge of the solar system like the edge of a map. You cross it and the color changes. Scientists did not quite think it would be that simple, but many models still suggested clear boundaries. What Voyager found instead was more like weather at sea. Nothing looked visible, yet the invisible conditions kept shifting around it. In December 2004, Voyager 1 crossed the termination shock at about 94 astronomical units from the Sun. That was one major boundary of the heliosphere, the huge bubble carved out by the solar wind. The expectation was a gradual slowing as the Sun's particles met resistance from interstellar space. What Voyager found was sharper and rougher, like hitting an unseen surf line in black water. The solar wind dropped from faster than sound speeds to slower ones. The magnetic field strengthened. Space, which people love to call empty, behaved more like a pressured frontier. Think of driving on a smooth road and suddenly rolling into deep gravel. The car is still moving, but every part of the ride starts talking back. That mattered because it meant the old picture of space as a quiet fade-out was wrong. Voyager was not drifting through nothing. It was crossing structures, layers, and forces. It was entering the heliosheath, the outer region where the sun still mattered, but not in the easy, confident way it does near Earth. Home was becoming a weaker voice. On your kitchen table, a weak voice is easy to understand. It is the radio at the far end of the house. It is the old flashlight when the batteries sag. That is what makes Voyager so easy to love. The same truth that governs a dying remote control also governs a machine 15 billion miles away. Power runs low. Choices get harder. Then came the great question. When would Voyager 1 leave the heliosphere and enter interstellar space, the region between stars? People kept saying the spacecraft had already left the solar system, but that phrase was messy and often wrong. The Voyager team was cautious. Ed Stone, the project scientist at Caltech, said they were dealing with one of the most important milestones in exploration, and they wanted the data first. In May 2012, something started to change. Galactic cosmic rays, particles from outside our solar bubble, jumped upward. At the same time, lower energy particles from inside the heliosphere began to drop. The expectation had been a clean set of signs arriving together, like matching lights on a control panel. What appeared instead was a clue with missing pieces, like hearing footsteps in a hall and not knowing which door opened. By July, the pattern sharpened. Then on August 25, 2012, Voyager 1 crossed into a new region for good. Inside, particles dropped by more than a factor of 1,000 from earlier levels. Galactic cosmic rays rose to the highest levels of the mission. If you had only those numbers, you might think the case was closed. But it was not closed, because one expected sign failed to show up. Scientists had long thought the direction of the magnetic field would swing sharply when Voyager passed from the sun's magnetic influence into the interstellar medium. Instead, the field direction changed by less than 2 degrees. The strength jumped by about 60%, but the direction hardly turned at all. That was a shock of a different kind. The textbooks had prepared everyone for a door. Voyager found a doorway where the smell of home still lingered in the next room. Ed Stone later said the path to interstellar space had been more complicated than anyone imagined. The spacecraft had reached a place no human-made object had reached before, and even then, the border refused to behave. Here is the strange beauty of that moment. Voyager 1's plasma instrument, the one best suited to measuring the density, speed, and temperature of plasma directly, had stopped working back in 1980. The expectation then was brutal. If the cleanest measuring tool was dead, maybe the final proof would stay out of reach. Maybe the most important crossing would remain a guess. Then the sun itself helped. In April 2013, Voyager's plasma wave instrument picked up local plasma oscillations, ripples in ionized gas around the spacecraft. Don Gurnett and Bill Kurth at the University of Iowa had been waiting for something like this. They realized a burst of solar activity from the year before had slammed outward and made the plasma around Voyager ring like a bell. The expectation had been silence. The finding was sound. The comparison almost writes itself. It was like being in a pitch-black cave and learning the shape of the walls from the echo of a shout. By tracking the pitch of those plasma waves, the team could infer the density of the surrounding plasma, and that density matched interstellar space. Even better, Gurnett and Kurth found an earlier, fainter set of oscillations buried in the data from late 2012. When they traced it back, the timing fit the August 25th crossing. The proof did not come from a photograph. It did not come from a lens. It came from a machine listening to the hum of matter between stars. That is the point where the meaning of the title starts to shift. The last photograph Voyager 1 would ever send back had already happened in 1990. But the last image in the deeper sense, the last portrait of where we live and what lies beyond, was still being assembled line by line from fields, particles, and waves. The spacecraft had stopped making pictures for our eyes and started making pictures for our minds. This is where scale flips on you again. A child can understand the basic move. If you shut your eyes in your bedroom, you are not gone from the room. You still feel the floor, the air, the blanket, the hum in the wall, the warmth near the window. Voyager was doing something like that, only the room was the border between the sun and the galaxy. As the years passed, that invisible portrait kept gaining detail. Voyager 1 measured cosmic rays. It measured magnetic fields. It listened to plasma waves. Piece by piece, it revealed that the outer edge of the sun's influence was not a simple shell with a neat label, but a strange, mixed region where expectations kept failing. Space was not cleaner there, it was more subtle, and the scientists did not pretend otherwise. Even after the 2012 crossing, there was room for hesitation. Stone himself said Voyager seemed to be in a mixed transitional region, bathed in matter from other stars, yet still showing some sign of solar influence. That small admission matters. Real discovery rarely arrives as a tidy speech. It arrives with one hand still raised. Months turned into years, and Voyager kept going. On Earth, newer missions came and went. Phones got brighter, screens got sharper, yet the farthest spacecraft humanity had ever built kept sending back a thinner, stranger kind of vision from a place nobody could visit. It did this with computers that NASA says process only about 8,000 instructions per second, less than a grain of dust beside a modern phone. Then, in November 2023, Voyager 1 seemed to stumble. It was still sending a radio signal, but the data inside it made no sense. The expectation honestly was grim. An old spacecraft, nearly half a century into flight, had begun talking nonsense from more than 15 billion miles away. That sounds like the sort of sentence that comes right before an obituary. But that was not the next line. In March 2024, NASA reported that one section of the spacecraft's flight data subsystem had started behaving differently after a carefully chosen command, a gentle poke. A Deep Space Network engineer was able to decode the odd signal and realized it contained a readout of the entire memory. Imagine shaking a locked mailbox across town and hearing one useful key rattle free. The problem appeared to involve corrupted memory in the system that packages engineering and science data before transmission. Engineers on Earth could not replace a chip. They could not even hurry. A radio command took about 22.5 hours to reach Voyager, and another 22.5 hours for the answer to come back. Every move was a 2-day breath held in public. In April 2024, the team tried something bold. They split the affected code into sections and moved those sections into different places in the spacecraft's memory, then updated all the references so the software could still act as one whole. The expectation had been that an ancient machine at interstellar distance would be too brittle to rescue this way. The finding was the opposite. Voyager answered with usable engineering data again. That fix feels almost impossible when you say it out loud. It is like editing a recipe inside a sealed oven from another continent, then waiting 2 days to see whether the cake rose. Yet it worked. The spacecraft's health became visible again. Later, its science data returned too. The invisible portrait continued. By then, the mission had become a lesson not just in science, but in patience. Voyager 1 was not winning because it was strong. It was winning because engineers and scientists kept making hard choices before disaster made the choices for them. Suzanne Dodd at JPL said in 2025 that the team wanted to keep the deep space rock stars going as long as possible, but electrical power was running low. That power comes from radioisotope thermoelectric generators, devices that turn the heat of decaying plutonium into electricity. Both Voyagers lose about 4 watts every year. 4 watts does not sound like much until you realize the margins are razor thin. 4 watts can become the difference between one more instrument and none, one more year and no more years, one more whisper and silence. So the mission kept subtracting to keep seeing. On February 25, 2025, engineers turned off Voyager 1's cosmic ray subsystem to save power. 3 science instruments remained active then. On April 17, 2026, they shut down the low-energy charged particles experiment too. Kareem Badarudin, Voyager mission manager at JPL, said it plainly. Nobody wants to turn off science, but it was the best option available. What remained on Voyager 1 after that were 2 instruments still doing excellent work, according to NASA. The magnetometer and the plasma wave subsystem. One measures magnetic fields, one listens to plasma waves. No camera, no colorful frame for your wall. And yet these are the tools still drawing the edge of our neighborhood with the kind of honesty a camera never could. The expectation near the end of a mission is usually narrowing. Less capability, less story, smaller meaning. Voyager keeps producing the reverse feeling. As the machine loses parts, the questions get bigger. The final image stops being a photograph of planets and becomes something wider, a portrait of the sun's fading reach, the texture of interstellar space, and the fact that the border between them is alive. Once you accept that, Voyager's future matters in a new way. We are no longer waiting for one last pretty picture. We are waiting for the last pieces of a map that only this machine can make. The questions ahead are not about whether Earth will appear again in a sunbeam. They are about how the sun's influence thins, bends, and finally gives way to the wider galaxy. That matters to science in a direct way. The heliosphere helps shield our part of space from some cosmic radiation. Learning its structure is not just abstract. It teaches us what kind of environment future deep space travelers may cross. It helps scientists test models of plasma, magnetic fields, and the long breath of the solar wind. It tells us what kind of bubble our star blows around our lives. By 2026, the engineering choices had become painfully exact. NASA's update on April 17, 2026 said Voyager 1 was more than 15 billion miles, or about 25 billion kilometers from Earth. A command took around 23 hours to arrive. The shutdown process for the low-energy charged particles experiment took about 3 hours and 15 minutes once the spacecraft received it. Even the timing felt delicate. That same update included an oddly hopeful detail. Part of the low-energy charged particles instrument, a small motor that spins the sensor, was left on because it uses only about 0.5 watts. The team wanted the best chance of turning the instrument back on someday if extra power could be found. Even near the edge of ending, the mission still makes room for return. NASA also described a more ambitious power-saving plan with a nickname that sounds almost comic beside the seriousness of the problem: the Big Bang. The idea was to swap out groups of powered devices at once, turning some things off and replacing them with lower power alternatives so the spacecraft could stay warm enough to keep working. Tests were planned on Voyager 2 in May and June 2026, with a possible try on Voyager 1 no sooner than July. That is what late-stage exploration looks like. Not a flag on a summit, not a hero speech. A team in Southern California studies voltage, heat, and delay, trying to protect fuel lines from freezing inside a machine launched when disco was new. The future of humanity's farthest explorer may hinge on fractions of a watt and the nerve to act before a fault protection system acts for you. Meanwhile, the distance keeps becoming more precise, almost poetic in its precision. NASA says Voyager 1 is on track to reach 1 light day from Earth on November 18, 2026, at 2:16:07 a.m. Pacific Time. That is 16,094,799,096 miles, or 25,902,068,356 kilometers. Light itself will need a full day to cross the gap. The machine will still be farther. Beyond that lies the truly long future. In the year 40,272, NASA says Voyager 1 will come within about 1.7 light-years of a star called AC plus 793888. Long after every person alive now is gone, long after our languages keep changing, the spacecraft will still be moving. It will not be useful in the way we measure usefulness. It will simply remain a fact. And that changes what the last image means. The final photograph from Voyager 1 was a tiny Earth in 1990. The final image in the broader sense is a much slower work, still arriving in fragments, built from magnetic fields, plasma waves, and the thin voice of an explorer crossing a region no camera could ever truly show. One image ended in a day, the other takes decades. Something else changes too. The old story made Voyager feel like a relic, a museum piece that happened to stay powered on. The fuller story makes it feel current. It is still part of the present tense. It is still testing ideas. It is still forcing living scientists and engineers to make new decisions on live data. It is still, in the strictest sense, out there, seeing. What comes next will not look cinematic from a distance. It may be another instrument shutdown. It may be a clever power fix that buys another year. It may be a fresh batch of plasma data that makes heliophysics papers argue all over again. It may simply be that November 18, 2026 milestone, when a human object reaches 1 light day from home and still has something to say. And after that, the horizon keeps moving. Maybe one remaining instrument works into the 2030s. Maybe an unexpected fault ends things sooner. Linda Spilker of JPL once put the feeling well when she said every day could be Voyager's last, but that day could also bring another interstellar revelation. That is not a slogan. That is the emotional truth of operating at the far edge. Soon, somebody somewhere will open a fresh dataset from Voyager 1 and see a pattern no one has noticed before. Soon, another hard power choice will be made by people who know they are caretakers of a voice nearly a day away. Soon, a milestone that sounded impossible in the 20th century will become a timestamp on a NASA page and then pass into history. So save this video and set yourself a reminder for November 18, 2026. When Voyager 1 reaches 1 light day from Earth, that date will mean more to you because you already know what kind of voice made it there. If you want one image to carry away, make it this. Not the bright posters of planets from the early years, and not even the pale blue pixel, though that one still matters. Picture a radio dish on Earth turning through the night while, a full day away at light speed, a worn machine hangs in the dark and sends back one more whisper about the shape of the sea between stars. That is the last image Voyager 1 will ever send us. Not one frozen frame, but a fading, truthful portrait built from the final things it can still feel. And if the history of this mission tells us anything, it is that the future will keep arriving that way for a while yet. Quiet, delayed, hard-won, and full of more wonder than the simple version ever promised.